Hello, this is Dr. Armand again, bringing you another exciting lecture in general chemistry. In this lecture, we'll be continuing talking about what occurs on the phase boundaries for the different phases, and also show you how you can cross different phases by adjusting the pressure and temperature of a substance. So sit back and relax and enjoy the show. So continuing with the vapor pressure and boiling point vapor pressure and boiling point that describes what occurs the liquid vapor equilibria. We'll be talking about boiling point. So what a boiling point is the temperature at which the vapor pressure equals the external pressure. And so you can have different boiling points for a substance because if you adjust the pressure, you can change the boiling point of a substance. Likewise, if you ever read on the cooking, when you go to higher altitude, it takes longer to cook because there's less pressure higher up. So that decreases the boiling point of water. So it takes longer to cook your food. So by changing the pressure, you can change the temperature of your boiling point of your substance. So for water, if you, for example, have water in a bell jar and reduce the pressure enough, you can make water boil at room temperature. Now, the boiling point that is very common to us is the normal boiling point. And so the normal boiling point of water is 100 degrees Celsius. And so normal boiling point, what that refers to is the boiling point at 1 atmosphere. So anytime you see normal in front of boiling point or melting point, it's referring to the temperature at 1 atmosphere of pressure. So the normal boiling point of water is 100 degrees Celsius. And most substances, when you look up their boiling point, you're looking up the normal boiling point of that substance. So again, normal means that it occurs at 1 atmosphere or 760 torr of pressure. Now, as you increase the external pressure of the liquid, you increase the boiling point because it takes more energy to remove the molecules from the surface of the liquid. So we also have solid liquid equilibrium and solid vapor. And so as you increase the temperature of your solid, you increase the kinetic energy within the molecules, which allows eventually for the particles to break free, and then melting begins. And over time of this solid liquid equilibria, you have an equilibrium between the melting of your solid and the freezing of your liquid. And so that's what occurs at the solid liquid equilibria. So it's this balance between melting and freezing. So the temperature at which the melting rate equals the freezing rate is the melting point. So whenever we refer to melting point, it's at a constant temperature. So when you melt something, the temperature of that substance remains the same until all of the substance is melted or all of the substance is froze. Now, just like with boiling point, we have the normal melting point, which is the melting point of 1 atmosphere. And for water, the normal melting point is 0 degrees Celsius. So most, anytime you read about a melting point of a substance, typically that's the normal melting point of that substance. And if you were to plot pressure versus temperature, it would give you an almost linear fit. So as you increase pressure, you're going to increase temperature of that substance. So that's what's occurring at the solid liquid equilibria. Now at the solid vapor equilibria, where we have sublimation and deposition. So sublimation is when we go from a gas to a liquid. So here, for example, we have sublimation. So for sublimation, we're going from a solid, to a gas. So there's no change in the going to the liquid. So we go directly from a solid to a gas. Some common things that sublime or dry ice, iodine vapor. So if you heat iodine and you have a cold finger, when the iodine vapor touches the cold finger, it deposits, so it sublimes when it's heated, and then when it hits the cold finger, it deposits onto the cold finger. So you get these iodine crystals on the cold finger. And these are for, very solids that have very weak attractive forces, intermolecular forces. So they have very low vapor pressures as well. And it doesn't take much to make the molecules leave each other after leaving the solid state. So they're very weak. You apply a little bit of heat, they leave, they become vapor because they have very weak attractive forces, intermolecular forces, and therefore you skip the liquid stage. You go directly from a solid to a gas. And these are for those substances with weak intermolecular forces, such things as carbon dioxide and iodine. And so what do we do with these phase boundaries? Typically we draw a chart, and that chart represents what occurs at different pressures and temperatures. This is referred to as a phase diagram. So phase diagrams is a plot of pressure and temperature, and it shows, okay, where the different phases are stable and where phase changes occur. And so what we're looking at is the phase diagram of CO2. So on the y-axis, we have pressure. It doesn't matter about the units. Typically, the pressures in atmospheres or torr. Temperature, again, it could be degrees Celsius or Kelvin. And so what you're looking at is the phase diagram. So we have three phases: solid, liquid, and gas. And so along the boundaries is where we have the phase changes. So between a solid and a liquid, we have melting and freezing. Between the liquid and the gas, we have vaporization and condensation occurring along this line. So along this line is where you have phase changes. Now, if you look here along the solid gas boundary, you have sublimation and deposition. Now, there are a few critical or a few key points on the phase diagram. The first point is the critical point. So the critical point is the temperature and pressure, where above this temperature you can no longer tell the difference between a liquid and a gas. It becomes a supercritical fluid. So the critical point for carbon dioxide is 31 degrees Celsius, 73 atmospheres. So above this temperature and pressure, it's going to have some properties of a liquid and some properties of a gas. And it's not really a liquid, it's not really a gas. They call it a supercritical fluid. And supercritical CO2 is used in a lot of industrial processes. So that's one key point, the critical point. Again, it's the pressure and temperature above which you cannot distinguish between a liquid and a vapor state. Another key point is the triple point. And so the triple point is the pressure and temperature where all three phases coexist. So for CO2, it's negative 57 degrees Celsius, 5.1 atmospheres. So again, the triple point is where all three phases coexist at a particular pressure and temperature. Now, one thing you have to notice is the solid liquid phase boundary. So since it has a positive slope, so again, since the liquid solid phase boundary has a positive slope, that tells you the solid is denser than the liquid. So here you see the solid liquid phase boundary has a positive slope. Solid is then denser than the liquid. If it was opposite, it had a negative slope, then the liquid would be denser than the solid. So again, some key things here. We have the critical point, the pressure and temperature above which you can no longer distinguish if it's a gas or a liquid. We have the triple point where all three phases coexist. And we have to investigate the solid liquid phase boundary. to see whether the solid is denser than the liquid or the liquid is denser than the solid by looking at the slope of the solid liquid phase boundary. Since it's a positive slope, the solid CO2 is more dense than a liquid CO2. Another thing we can look at are the normal boiling point and melting point. But as we see here, CO2 has no normal boiling point or melting point. Because again, to be normal boiling point and melting point, we have to be at 1 atmosphere. And you see here, 1 atmosphere, it never crosses the solid liquid or liquid gas, boundary. So at 1 atmosphere, the only thing that CO2 can do is sublime or undergo deposition. You have to increase the pressure above 5.1 atmospheres or right at 5.1 atmospheres to where you can get a solid to melt into the liquid. So above 5.1 atmospheres, you can have a solid melt into liquid CO2. And then you can also have it vaporize. But for normal melting and boiling point, CO2 does not undergo that because at 1 atmosphere, it does not cross the solid liquid or liquid vapor boundaries. So here's the phase diagram for H2O, just to look at a few key things on that. So we have the critical point. You see the critical point for H2O is a lot higher temperature and pressure than CO2. It's 374 degrees Celsius, 218 atmospheres. So it takes a lot of pressure and a lot of heat to make supercritical H2O. And again, above this temperature and pressure is where you would have a supercritical fluid. You couldn't distinguish between if it's a gas or liquid. Likewise, we have the triple point of water, and it's at almost 0 degrees Celsius and 0.006 atmospheres. So again, triple point of water is where all 3 phases coexist. And now if we look at 1 atmosphere, we see that the 1 atmosphere crosses the solid liquid phase boundary at approximately 0 degrees Celsius. So 0 degrees Celsius is the normal boiling point, because it's just a smidge to the left of the triple point. And the triple point is 0.01 degrees Celsius, so you can imagine that the melting point is 0 degrees Celsius. Now, if we continue along the 1 atmosphere, you see we cross the liquid vapor boundary. And that's going to be the normal boiling point. So this is the normal melting point, 0 degrees Celsius. And normal boiling point is 100 degrees Celsius. Because again, the 1 atmosphere crosses the solid liquid and liquid vapor boundary. So this is the normal boiling point. Now, if we reduce the pressure almost close to 0 atmospheres, you see that we can reduce the temperature at which water boils. And so that's what you're seeing here. As you decrease the pressure, you're going to decrease the temperature, in which case there's less heat to cook your food. Now, if we reduce the pressure of water or of our substance, say the solid, so if we do reduce the pressure of ice below 0.006 atmospheres, then we can undergo sublimation and deposition. So it takes a very low pressure and very cold temperature to sublime water. Naturally, water exists as a solid and liquid at normal pressure, and then of course a gas. Likewise, you see that the solid liquid boundary has a negative slope, which indicates the liquid is denser than the solid. So that's what you want to watch out for. You look at the solid liquid phase boundary. You see, is it negative or is it positive? If it's negative, the liquid is denser than the solid. If it's positive, the solid is denser than the liquid. So if we were at 150 degrees Celsius, we would only be crossing, for example, the gas liquid phase boundary. So we'd only be undergoing vaporization. But if we were at -1 degrees Celsius, for example, we could undergo sublimation deposition, and also we could undergo melting and freezing at -1 degree Celsius by adjusting the pressure. So now we want to ask a few questions involving the phase diagrams. And so here we're using CO2's phase diagram. And we have a still, so carbon dioxide is sold in still cylinders under a pressure of approximately 20 atmospheres. They want to know at 20 atmospheres, is there liquid carbon dioxide at the following temperatures: 20 degrees Celsius, 40 degrees Celsius, -40 degrees Celsius, and -120 degrees Celsius. So we have this carbon dioxide in a still cylinder under a pressure of 20 atmospheres. So we want to know at the different temperatures, would there be any liquid carbon dioxide present? So first off, what we need to do is determine where 20 atmospheres is. So the critical point is at 73 atmospheres. That's about there. The triple point is at 5 atmospheres, which is about there. And if we were to approximate where 20 would be, I would have to say 20 atmospheres, maybe right about here. So this green line represents 20 atmospheres. It'd be closer to 5 than it would 73. So that's where 20 atmospheres is, and it's saying, okay, at 20 degrees Celsius. So again, if we look at the triple point, is -57 degrees Celsius. And at the critical point, we're at 31 degrees Celsius. To give us an idea of where our temperatures are. So at 20 degrees Celsius and 20 atmospheres, so 20 degrees Celsius, and it's all approximation. So 20 degrees Celsius, let's do some. So where would 20 degrees Celsius? It'd be close to 31. Let's see. And I would approximate 20 degrees Celsius to be maybe right about here. So at 20 atmospheres and 20 degrees Celsius, would we have liquid CO2? The answer is, based on our approximations, the answer would be no. We'll put an N for no. At 40 degrees Celsius, it would be no, because 40 degrees Celsius would be out here and it would be in the vapor state. So that would be no. What about -40 degrees Celsius? So now we look at, so this was 20 degrees Celsius. What about -40 degrees Celsius? And negative 40 degrees Celsius would be right about, somewhere right about here. And negative 40 degrees Celsius could exist, maybe would have liquid CO2. So that would be, yes. Now, negative 120 degrees Celsius would be lower than negative 78, so that would be no, it would be in the solid state. Okay. So that was the answers to number 1. Now, in B, if chunks of dry ice, carbon dioxide, so these are chunks, these are solids, are warmed by leaving them in an open container at room temperature, will they melt? So open container means it's at roughly 1 atmosphere. That means it's, atmospheric pressure, which is approximately 1 atmosphere. And it's at room temp, will they melt? So if we look at 1 atmosphere, so we draw a line along 1 atmosphere. At 20 degrees Celsius, will they melt? The answer is no, because at 20 degrees Celsius, it's in the vapor state at 1 atmosphere. So therefore, it would sublime. So the answer to this is no, it would not melt. Because again, as you go along 1 atmosphere, when it crosses 20 degrees Celsius, it's going to be in a vapor, and the only phase boundaries it crosses is solid to gas. So this dry ice would sublime. All right. Now moving to see if a container was nearly filled with dry ice and then sealed and warmed to room temperature, will the ice melt? So here again, we'll assume room temperature is again 20 degrees Celsius. Now the difference here is it's sealed, so as you're warming it, the pressure is going to increase. So if you have dry ice and as you warm it, the pressure would increase. Will the ice melt? Yes, eventually if the pressure gets above, this point here, which is probably about, I would say, 40 atmospheres, then it would melt. So again, the temperature is constant, but now since it's in a sealed container, the pressure is going to increase. And if you increase the pressure enough at 20 degrees Celsius, you will get liquid CO2. So then if you increase the pressure enough, you will have the dry ice melt. So the answer is, for this one, is yes, it will melt. Once you build up enough pressure, the solid would melt into the liquid. And then lastly, if dry ice was compressed at a temperature below its triple point, will it melt? So the triple point is here. You see we have a positive slope. So as you compress it, the pressure increases. But if you increase the pressure of the solid below the triple point, it will never undergo melting. It'll always undergo deposition or sublimation. Because again, if we draw a line here, let me pick a different color. So at the triple point, we draw a straight line. We see that as we increase, if we're at a lower temperature than the triple point, as we increase the pressure of the dry ice, it will never melt. So from negative 57 to whatever the end point is, say negative 300, at anywhere along this line, as if we increase the pressure, by compressing it, it will not undergo melting. The answer would be no. So that's how you utilize the phase diagram to answer these types of questions. Here's another one. We have a phase diagram of carbon, and we have a few questions we're going to answer. So again, at certain pressure and temperature, you have diamond, there's liquid carbon, carbon vapor, and graphite / metastable diamond, and then diamond and metastable graphite, and then you have graphite here. So most of this is solid with just different forms of carbon. And so what you notice here is that for carbon, we just have a triple point given to us here. And the triple point of carbon would only involve graphite, carbon vapor, and carbon liquid. There is no critical point given on this graph. And so the first question asks, is there any temperature at which diamond can be vaporized? So we look diamond to be vaporized, it has to cross the liquid vapor liquid or the vapor boundary. And as you see, diamond never crosses the vapor boundary, so it cannot be vaporized. Diamond can melt into carbon liquid, but then carbon liquid is vaporized into carbon vapor. But diamond cannot directly vaporize into a carbon vapor because it never touches the vapor boundary. So the only thing diamond can do is diamond can melt into a carbon liquid, or if you decrease the pressure enough on diamond, you can turn it into graphite at particular temperatures. But there's nowhere that diamond touches the vapor boundary, so diamond cannot be vaporized. So the answer is no. Now graphite can be vaporized. And the reason graphite can be vaporized is if you look here, let me delete a few things. If you look here, graphite crosses or touches the vapor boundary. So graphite can be vaporized at a very low pressure and temperature because again, it touches the vapor boundary. So graphite can be vaporized, but diamond cannot. Now, what's the approximate temperature at which carbon vapor will undergo deposition? So again, deposition, what does that mean? That means that we're going from a vapor to a solid. Deposition means vapor to solid. So is there anywhere that we can undergo directly from carbon vapor to a solid? And if we look here, and my bad word in temperature is in the 1,000 Kelvin, so this is like 4,000 Kelvin, 6,000 Kelvin, 8,000 Kelvin, 2,000 Kelvin. So to get from diamond to graphite, you have to, at a, say, 23,000 Kelvin, reduce the pressure. But back to this question. So what is the approximate temperature at which carbon will undergo deposition? So the triple point is 4,600, and this right here is 4,000. So if we put, and so between 4,600 and 4,000 at very low, and this pressure again is in gigapascals, so it's a low-ish pressure in reference to carbon. But so 0.01 gigapascals to 0.001 gigapascals between a temperature of 4,000 to 4,600 Kelvin. So the approximate temperature at which carbon will undergo deposition would be approximately, 4,500 Kelvin. So that's the approximate temperature at a particular, at the right pressure, will undergo deposition. So anywhere along this solid liquid or this graphite vapor boundary is where it would undergo deposition. So approximately, 4,500 Kelvin at a pressure of about 0.005 gigapascals. So that's all for the lecture on phase diagrams. Hopefully that you understand how we use phase diagrams to see if any type of particular phase transition can be undergone. So for example, if we have water at a certain pressure, can it undergo sublimation? Or if we have carbon dioxide at a certain temperature, what phases could it exist as at different pressures? Or if we want to know what's the triple point of a substance or the critical point of a substance, we would use phase diagrams. So on that note, that's all I have for today. So until next time, Dr. Armand signing off.